for having me, and thanks to all of you for sticking around till the end. I hope I can provide some light entertainment. So at the end of Jung's beautiful talk this morning, he raised an open question, which is, can we find a systematic way to look for, to explore otherwise unspecified conformal field theories in the fuzzy sphere? And well, let's say that the goal of this talk is to work towards that. Yeah, I won't quite. We haven't quite succeeded yet, but that's, yeah, it's in that direction. So the title of the talk involves the phrase entanglement bootstrap, and I think I probably have to explain what that is, since I didn't make it up, but yeah, my friends made it up. And so entanglement bootstrap is let's say it's a research program guided by the following vague idea. I called it central dogma, which is the statement that all of the universal properties of a state of matter are encoded in the reduced density matrix of a ball in a single representative wave function. Okay, that's the statement. And let me define what I mean by the word universal for the purposes of this talk. It's a somewhat limited definition to mean properties of a RG fixed point. We could argue about whether that's the right definition, but that's what I mean by it here. And so since it's a property of the fixed point, it's something that's true in every state that flows to that fixed point. Right, so everything in the basin of attraction of the fixed point. And oh yeah, I should explain the term central dogma is borrowed from the molecular biologists. Right, so Francis Crick used this term to refer to the sort of guiding idea, sort of question-generating idea that, in their case, it was the idea that DNA leads to RNA, leads to proteins, and in particular that every cell of a living organism contains the complete instructions for recreating the whole organism. Okay, so I think it's a good name for this idea because it's sort of a similar statement that in a many-body state, looking at just a small, well, not necessarily small, some local region of the many-body state allows you to reconstruct the whole state and yeah, everything you might want to know about it. Okay, everything I might want to know about it. Yeah, that's an important pronoun. Okay, so I should spend some time telling you why I believe this statement before, why I'm using it as a guide for my research program. And so I'm going to make a series of statements whose goal is to first to give some idea of why we should think that the central dogma is true, and secondly, to provide some context for the kinds of things we'll do. And yeah, so this is a disclaimer here. So the statements I'm about to make are not mathematical physics statements. They're the kinds of statements that mathematical physicists would like to prove. Would like to find some assumptions which make these statements true. When I say the statements, what I mean is usually they're true. And when they're not, the question of when they're not true is a more delicate thing that we can talk about later. There definitely are times when they're not true. So, okay, so the first statement is that in the ground state of a local Hamiltonian, this word local is very, very important. It's totally crucial, for example, to avoid the kinds of counterexamples that Mykola mentioned yesterday. So if you add non-local terms to the Hamiltonian, you can totally destroy everything I'm saying. So that's not allowed. And so yeah, in the ground state of a local Hamiltonian, there's the entanglement entropy, the very basic property of our reduced density matrix of the ball, satisfies an area law. In particular, its contributions come from the boundary. There's local entanglement between the degrees of freedom near the boundary and on the inside and on the outside of the ball. Okay, so this isn't exactly always true, but it's generally true. A second statement is so from that you can tell whether whether the state you're starting with is a ground state. The second statement is you can tell whether the state is gapped or not.
Without logarithmic corrections?
There can be logs. Yeah, that's an example of an interesting exception. Yeah, right, indeed.
That will not be allowed.
It's allowed. Okay. Yeah, so ground state of a CFT in 1 + 1 dimensions has log corrections. Yeah. So in particular, we can tell whether it's gapped or not because we can compute correlation functions of local operators inside the ball. And well, if we can see exponential decay, then there's a correlation length smaller than the size of the ball. It's probably gapped. And if we don't, then if there's some power law we can read off within our ball, then it's probably gapless. So notice that this is exactly the reason that I'm, for my limited definition of the word universal, if you have some, if the system is described by some, I don't know, some, say, free scalar field with a very small mass, then this is hard to do, right? You won't be able to see the crossover from the massless theory to nothing in a small ball. Okay, and then next, in a certain class of gapped ground states, namely those with liquid topological order, we can make a more refined statement about the area law of the entanglement entropy. In particular, in addition to this area law term, okay, let me try to point at the area law term there. There's the area law. There's a subleading correction, which is universal. So the coefficient of the area law is garbage. This epsilon is like the lattice spacing, something like that. But this subleading term is a universal thing, which depends on the anion content of the theory. It counts some count of how many anyons there are, and that data about the anyons is a label on the phase that can't change within the phase. It only changes when across a phase transition. Okay, so yeah, the list goes on. I want to really convince you that this is true. So as Fokker mentioned, there are Hamiltonians, local Hamiltonians, whose ground state has a logarithmic violation of the area law. An example that'll be very important is 1 + 1 dimensional conformal field theory, where instead an area in one dimension would be just constant, independent of the size of the ball, but instead it goes like log of the size of the ball, and the coefficient of that log is a piece of universal information, namely the central charge, a measure of the number of degrees of freedom of our CFT. And there's a similar formula for the special case of round balls in higher dimensions. So in 1 + 1 dimensions, every ball is round. But in higher dimensions, this is a restriction. And only for round balls do we know the answer. And similarly, there's a RG monotone that appears in the entanglement entropy of round balls. Okay, but all the examples I've given so far, I just said something about the entanglement entropy. Right? The entanglement entropy is just it's a number, but the thing we're allowing ourselves in this dogma is the whole reduced density matrix of the ball, which is an operator on some Hilbert space. There's a lot more in it than just the von Neumann entropy, and so in particular, it's useful to organize that information by taking minus the log of the density matrix, so that the density matrix looks like a Gibbs state for this. This is just a tautological statement. It looks like a Gibbs state for this so-called entanglement Hamiltonian. And then we can do some things with that operator, with that entanglement Hamiltonian. In particular, we can think about, say, in a 2 + 1 dimensional gapped state, we can think about dividing up our ball into 3 regions like this, and computing the commutator of the entanglement Hamiltonian for AB and for BC, and taking the expectation value in the state that we're given. And these folks argued that this is a measure of the chiral central charge of that state. So the number of left-moving modes minus the number of right-moving edge modes that are forced to be there at some boundary at some physical boundary of that state. And I guess this is maybe let's say this is part of a conjecture due to Lee and Haldane that the reduced density matrix of a ball in the middle of in the bulk of such a state knows about the spectrum of the CFT at the edge that appears at the edge of such a state.
Is there some heuristic reason why that's true?
The modular commutator. Well, okay, a sort of. It's a bit of a long story. Yeah.
Is it true in any dimension?
This is special to 2 + 1 dimensions.
Okay. Yeah. Is it something that people who do like exact legalization, fractional flow, they can test this?
Yes. The answer is yes.
And
yes.
They tested it?
Yes. Well, the people who tested it were these people whose main job is not doing the exact analyzation of fractional quantum Hall, but they did test it, and yes, it seems to be true. Yeah. By the way, like in nearly every statement I've made here, there are ways to make it wrong, right? So an antagonist could come along and act on this state with some local unitaries and mess up this relation a little bit. Yeah. but I'll tell you some assumptions under which they cannot. Okay.
Just a moment.
Yes,
yeah, for the central dogma, what do you mean by a single representative density matrix?
Yeah, I just mean
any density matrix, or
so by representative I mean some point in the phase or in the basin in the critical manifold of the fixed point. So just some state that flows to the fixed point of interest. That's what I mean by representative. Yeah. Okay, good. So just to convey that the dogma is actually a pretty broad idea. So far I've only talked about ground states, but I think it's worth mentioning that that ETH, which is our best understanding of why quantum statistical mechanics works, fits actually very nicely with this idea. Namely, one version of ETH is the statement that if you take a local Hamiltonian, find a single eigenstate of that Hamiltonian in the middle of the spectrum, so some finite energy density eigenstate, the statement is that by studying the reduced density matrix of that thing in the ball, you can reconstruct the whole Hamiltonian. So more specifically, that reduced density matrix is very well approximated by a Gibbs state using the actual Hamiltonian on that ball. And and in fact this is true, as was shown by Garrison and Grover, that this is true even when the region A is as much as half of the system. So it's not just a statement about local operators. It's true, for even half the system. And here's a picture of the eigenvectors, overlap between eigenvectors of the Gibbs state versus eigenvectors of the reduced density matrix. And yeah, the overlap is actually very impressive. So yeah, the statement is from the reduced density matrix of the ball, you can find the whole Hamiltonian, right? So in particular, if you know the Hamiltonian, you know anything anybody could ask about the state, not just the universal information. Okay. All right, so I think, okay, I'm done trying to convince you that the central dogma is true. Does everybody believe it now? You believe it? Yeah. Okay. So
the last thing, like what boundary conditions do you impose, I guess, are there?
Yeah, there's some stuff that happens at the boundary. That's right. It's very important that the Hamiltonian is local, so then we don't really care about what happens at the boundary too much. Yeah. Yeah, I mean, as always, when you make an entanglement cut, you're making a choice of boundary condition, but it's kind of always the same choice. Yeah. Okay. So a consequence, once we believe this, a consequence of this dogma is that for each category of state, whether if the state is a ground state of liquid topological order, if it's the ground state of a CFT, if it's some finite energy density state in the middle of the spectrum, for each category of state, we should be able to tell from the reduced density matrix of a ball which category it is, right? Is it a liquid topological order state? Is it something else? And so it seems like a good idea to try to identify what these conditions are for each category of states. And then if we know, we can find some necessary and sufficient conditions for the reduced density matrix to come from, say, the ground state of the CFT. There are two things we can do with it, which I think each of which could be called bootstrap. The first one is we could use those conditions as axioms, and then prove structural properties of the properties of the universal data that has to be true for every possible realization of that category of state. And the second thing we could do is we could just within small Hilbert spaces we could look for states that satisfy those conditions. Okay, so this seems like a good idea, I think. And so the goal of this entanglement bootstrap program is to understand the structure of the universal information, what relations among pieces of data there should be, what is the universal information, and learn to extract it from the density matrix. And I guess it's maybe important for me to mention that this leads to a certain perspective on quantum field theory. And the reason for that is that the universal information about, I haven't said what it is yet, but I think you'll all agree that usually it's encoded in a quantum field theory of some kind, like a conformal field theory or a topological field theory, something like that. And so in this way, we can learn something about quantum field theory by asking these questions. All right, so I want to talk about three categories of states in this talk. The first one is liquid topological order. I'll say more precisely what I mean by that, where actually it's the first mode of operation that has mostly been taken, namely finding some conditions, using them as axioms and proving things about the structural properties of the universal information. And then I'll talk about trying to extend this strategy to CFT. In 1 + 1 dimensions, I think we know what we're doing. In higher dimensions, I guess let's say it's, what is the word you use? Preliminary. Yeah, preliminary work, which we haven't yet written up. Okay, and there are a few other categories of states for which the strategy has been applied with some success. Okay, so I want to try to, so I promised myself I would not spend the whole talk talking about topological order. It's happened to me before. So I'm going to try very hard to be brief. Okay, what do I mean by topological order? I mean a gap phase of matter that's not continuously connected to a trivial state because it has local excitations that you can't create by any local operator. So these are usually called anyons. And what I mean by the properties of these local excitations, because they're not created by any local operator, they can have weird quantum numbers. And those weird quantum numbers are labels on the phase that distinguish it from the trivial phase. What I mean by liquid is that set of anyons doesn't depend on the geometry. So if you change the system size, the number of superselection sectors of anyons doesn't change. And this word is intended to rule out fractons, which are a class of topological order states which are more complicated and which we don't understand yet. Okay, so under exactly these assumptions, so this liquid topological order is the situation where we expect the low energy theory to be governed by a topological field theory. And topological field theory is a thing that mathematicians have strong opinions about what it is, and whether the mathematicians' opinions about what topological field theory is are the right opinions to govern low energy description of phases, such gap phases of matter, is an open question, right? That's a question that we can try to answer. That is, okay. That's roughly the goal. And the first question one needs to answer is, what is the condition on the reduced density matrix that it indeed comes from a state with liquid topological order? And this question was answered very beautifully by Bowen Shi and Kotaro Kato and Isaac Kim. And actually, the condition is very simple. There's two conditions on the entropy of balls. So I want you to think of these balls as not the big ball that I've been talking about, but some small part of it. And the condition is that for each ball of, say, a few lattice sites, if you divide it up in this way, so in both cases you're dividing up the ball into its interior and some boundary of the ball, and then studying some linear combination of entropies of the parts, right? So linear combination of the entropies of the parts. And the statement is that if the state satisfies that if this combination of entropies vanishes for every such small ball, then it's the ground state of some liquid topological order, Hamiltonian. A remarkable property of these conditions is that they're self-reproducing. So if this condition is true for small balls, it's also true for any larger ball. So to get some intuition for them, the first statement is that this A0 condition immediately implies an area law for round balls, because you see if this combination is 0, we can take C to be most of the ball, so that B is like just a thickened boundary. And then, so this relation is by subtraction, and this relation is by positivity of SBC. So you see the entropy of the whole thing is bounded above by the entropy of the thickened boundary. And then combining A0 and A1 implies an area law for every region, and in particular with a subleading term that's independent of the shape of the region.
Okay, so where is this independence of the region comes from? Because in both A0 and A1 you drew very particular shapes. Mm-hmm. We shouldn't be paying attention to the shapes. We should be just paying attention to topology.
Yes, that's right. But actually so you can fix the shape at the smallest sizes, and then the statement is that for larger things the shape doesn't matter. So you can deform a larger shape by, let's see. So suppose you're studying so your region is this, by attaching to it a small thing of a fixed shape. Let me do this. Suppose, I'm allowed to do that. I can replace it with this thing. So I'm quickly summarizing how these axioms are used to, how to show that bigger on
But you really insist that in this A0, A1, I should be just taking circles, or should I be taking any regions? What is the precise?
Yeah, okay. A simple statement is, if I demand that this is true for every region, every, say, small region of this topology, then then everything will follow. But actually, one can make a weaker assumption. For example, one could start with a lattice model, and only assume these things on, say, this is. We could think about some. Here's 7 sites, and what I mean by A0 is these combinations of sites. Yeah, that's okay. Both this combination and also this one.
Well, what is the axiom then? If your initial axioms assume that all sets involved are small, then what is the axiom which will allow you to increase the size? You have to have some axiom which involves large sets, otherwise.
No. This step is very important, right? So if the axiom is true for every small region, then by overlapping small regions, you can show that it's also true for.
Yeah, but there should be some axiom which allows you to overlap regions. Is it some other axiom that you don't write?
It's true for every small region, right? So in particular, it's true for this region, and then it's also true for this region, and so roughly you can combine them into a larger region. Yeah. Okay. Good. And but okay. I don't want to get into the weeds here, but I do want to try to convey the machinery, the idea of the machinery by which one can show things using these assumptions. Maybe the important thing is to say is that this condition A1 implies that conditional mutual informations vanish. It implies that if I take any 3 regions where ABC, where B is a buffer between A and C, then the conditional mutual information between A and C vanishes. That is, they form a quantum Markov chain. And a quantum Markov chain is a quantum generalization of the classical Markov chain. Classical Markov chain means you can reconstruct the joint density matrix from its marginals. And a quantum Markov chain is a similar thing. It means that you can reconstruct the density matrix of ABC uniquely from the density matrix of AB and the density matrix of BC. And in general, if I just hand you 2 density matrices, rho AB and rho BC, which agree on B, this is an extremely difficult problem to reconstruct the density matrix on rho AB. In general, it doesn't exist. But this Markov condition is a sufficient and necessary. Yeah, it's a sufficient condition for merging regions. Okay. So something that you can see also is that A0 implies that the mutual information between any region A outside this ball and the creamy filling C vanishes. Right? So this is a statement which is it's a very strong statement because the mutual information between A and C bounds from above any correlations of operators in A and C. So in particular, it says that the correlation length of the state is exactly 0. Right? So this is definitely too strong a condition. If I wanted to say that, this is too strong a condition to impose on any representative of a phase, it's rather a condition for the 0 correlation length fixed point. Right? So if here's my phase diagram, here's the basin of attraction of this fixed point, here's the basin of attraction of this fixed point, only the fixed point will exactly satisfy these axioms. The picture I want you to have in mind is based on the RG. If I pick some other representative of the phase, the axioms are violated on some small balls. But if I coarse grain a little bit, that is, if I study larger regions, the axioms will become more true. And so the expectation is that assuming approximate versions of the axioms would be enough to study an arbitrary point in the phase by a series of coarse graining steps. Okay, so I'm not going to tell you how, but these folks, the same people that proposed the axioms, showed that actually much of the structure of topological field theory can be derived from these assumptions. So in particular, we can identify the anion types, their quantum dimensions, their fusion rules, a non-degenerate S matrix. maybe briefly I'll say that the key engine of progress is a notion called information convex set, which is a machine that takes as input a state satisfying the axioms and a choice of region, which is part of our big ball. And the output is the set of density matrices that are consistent with the given state on every little ball inside the region. And this is an interesting thing because anyons are created by non-local operators. The part of the operator away from its boundaries is topological. That is, you can deform it, it doesn't change the answer. But if you put an anyon inside this annulus, the state of the annulus is necessarily different, globally different from the state if you didn't put the anyon. But locally, because you can deform the string away from any ball, it's the same. Okay, so that's the rough idea. The same axioms work in any dimension. And although in 2 + 1 dimensions, I would say we have a clear understanding of what the rate framework for incorporating the universal data is, namely some kind of modular tensor category. In higher dimensions, it's somewhat less clear what information you have to specify to completely specify which topological state you're talking about.
Sorry, with these axioms, you always get a finite number of anyons?
If the local Hilbert space dimension is finite. Yeah. And related to that, there is a bit of tension, of interesting and important tension between exactly satisfying these axioms and having ungappable boundaries, like for example, having a non-zero chiral central charge. In fact, we can prove that you can't simultaneously have exact A1, non-zero chiral central charge, and finite local Hilbert space dimension. Yeah, so this is an actual very interesting tension, a consequence of which is that there's a sense in which such states are actually not topological, in the sense that they know about the metric of the space that they're living on actually in a universal way. Okay, so okay, good. I promised I wouldn't say too much about the gapped case. That was probably a bit unsatisfying, but the message I wanted to convey is that there is a case where this program has sort of successfully been implemented and good things were done with it. So maybe it's not a crazy point of view. Okay, so now I want to talk about trying to use the same logic to learn about 1 + 1 dimensional CFT. So for those of you who don't care about topological phases, you can wake up now. We're going to totally start over. Okay. So here's the central dogma. Like I said, if it's really possible to extract all the universal information from the reduced density matrix of a ball, notice, by the way, I haven't said what the universal information is, right? Yeah, what I mean by that. And I'll rectify that in just a minute.
Basically, since we are now going to CFT, so there was some point in your introduction where you said that, okay, suppose that I have this ball, then I can measure correlation function within the ball. And if it looks like it's a parallel within the ball, then my best guess, if the ball is large enough, then it's a CFT.
Because I want to rule out crossovers. Yeah. So the thing I'm studying is the UV CFT.
It means that you have to have access not just to a single ball, but to a family of balls of larger and larger radius.
Well, right. So that's exactly why I made this restricted definition of what I meant by universal. I don't want to study crossovers between fixed points, right? So within the ball, I can study the UV fixed point.
But as we discussed in this conference, sometimes you have these theories which are going to look like a CFT up to a ball of size 400.
Okay.
So
I don't know how to study complex fixed points yet. Yeah. Yeah. Let's talk about that. Good.
Okay. So your best guess is if it looks like a CFT in a single ball, then it's probably a CFT.
That's where we are. Okay. So what's the condition for it to be a CFT? So as we already mentioned, the entropy of an interval is log of the size of the interval times the central charge. But actually there are states which have this property that are not ground states of CFTs. There are ground states even of local Hamiltonians that are not ground states of CFTs. I'm thinking of the Modskin chain. So that's not quite enough to specify what kind of state we're talking about. But as we said, the reduced density matrix has a lot more information than just the entropy. And in fact, for the case of a single interval in the ground state of a 1 + 1 dimensional CFT, we actually know the form of the entanglement Hamiltonian in terms of the stress tensor of the CFT. It's essentially a consequence of the Bisignano-Wicklund theorem, which is true for any relativistic theory. We know the entanglement Hamiltonian for a half space is the boost operator. And then in a CFT, the half space is related by a conformal transformation to a round ball, which, as we said, is in 1 + 1 dimensions is just an interval. And the boost operator is x times the Hamiltonian. And under the conformal transformation, that x maps to this function. It's just a quadratic function. It's only non-zero in the interval. It vanishes linearly at the ends. And so the entangled Hamiltonian is this coolness function, I'll call it, times the actual Hamiltonian density of the CFT plus some C number term, which is responsible for the expectation value of K, which is the entropy. OK, so knowing this, there's some quite remarkable conditions that the ground state of a CFT satisfies. And the key idea was actually, it was my student David Lin who had this beautiful idea, is just to think of these functions as a basis of functions. Let's talk about it on the line. We could talk about it on the interval. They're related by a conformal transformation. Let's think about these as a basis of functions on the line. And the idea is, with that basis of functions, we can make 0. So the precise statement is, think about three consecutive intervals bounded by these points. These are the things I'm drawing here are the functions beta associated to various combinations of those intervals. So the red one is beta ABC, the blue one here is beta A, and so on. And the statement is that if you add up this particular linear combination of those functions, it's identically 0. So it's not hard to see, right? They're each just polynomials in x. So you just need to cancel 3 coefficients. And so it's not so, OK. And you believe it? It's plausible, right? I mean, yeah, you can check it. Yeah, good. And eta, I didn't say what eta was. Eta is the cross ratio of those 4 points. All right? So it's a conformal invariant combination of those 4 points. And so a consequence of this is that the exact CFT entanglement Hamiltonian, entanglement Hamiltonians for these regions, if I add them all up, the operator part of each of them cancels out. Right? The coefficient, the betas all add up to 0. And so the operator part is 0. The only thing that's left is the entropy parts, which you can check that if you add those up, the thing you get is C/3 times this binary entropy function. Right? H of eta, just as if eta were a probability of a 2-state random variable. OK, so this is a very strong condition on the reduced density matrix of ABC, that if you divide up the region into these 3 parts, this combination of operators acts as a C number. OK. So far I've been writing formulae just in the continuum. I guess I should mention there's now a sect, a religious sect of people who don't believe that the things I'm talking about exist. All right? People who work on like algebraic quantum field theory say their main job in life is to identify which kind of von Neumann algebra a given system is described by, and the 3 types of von Neumann algebras are distinguished by which objects you're not allowed to talk about. Right? So as the number increases, you lose the privilege to talk about first the entropy, and then the reduced density matrix. Maybe I got the order wrong. So this is I'm saying very heretical things, and I will suffer for that in just a minute. But OK, so far I've been writing formulae in the continuum, and the thing I want to do is say something about well-regulated quantum field theories, right? I want to say something about tensor product Hilbert spaces of finite dimensional Hilbert spaces, tensor products of finite dimensional Hilbert spaces. And so to compare what I've said so far with that, let me divide up the circle or the line into equally spaced intervals, and let me regard each of those intervals as a site. Right, so I'm doing a slightly scary thing here, because each of those sites, of course, is described by an infinite dimensional Hilbert space if we're in the continuum. Right, there's infinitely many points in here, and OK, and yeah. So now I can ask the question: if I regard these A, B, and C as made up of some number of sites, each of which is a finite dimensional Hilbert space. For example, suppose I get my wave function from the ground state of some quantum critical Hamiltonian. Is this condition satisfied? And the answer to that question is no. And there's a simple way to see that that's true, because in any system with a finite dimensional local Hilbert space, if I think about the reduced density matrix of some region that's less than half the system, it has the same spectrum as the reduced density matrix of its complement, right? Because it's determined by the Schmidt eigenvalues of the whole density matrix. The whole state is pure. They have the same Schmidt eigenvalues, but its complement is bigger, right? So that means that one of them has to have a kernel, right? The bigger one has to have zero. Rho has to have 0 eigenvalues, and then when I take the log, k is the log of rho, I get nonsense, right? I take the log of 0, I get nonsense, and so necessarily, in any finite dimensional Hilbert space, there's some zeros of 0 eigenvalues of rho, which make this combination of things not so nice. And this is
but you said it's only the bigger part is going to have zeros, but what if you just stick to small intervals?
Well, okay, so there's a
I don't know if it's a valid question.
Don't worry, I'll fix it. Okay. Don't worry. Yeah. So the way around this is the following: if instead I act with the density matrix on the state, here we go. Act with k on the state, the kernel of rho just doesn't matter, right? Because the reason that it has 0 eigenvalues is because it kills the state, right? And so a thing that is true is take the equation that I wrote before, this operator equation, and just act both sides on the state that we started with. So this is a weaker condition, but it's actually true. It's actually true in lattice models, in quantum critical lattice models. But I want to emphasize, so I'm going to call this the vector fixed point equation. It's a very strong constraint on the state, right? It's n equations on, if my Hilbert space is n dimensional, it's n equations on the n components of the wave function. And it should be true for every combination of ABC. So it's actually very surprising that there are any solutions of it at all, if I impose this condition on every ABC collection of successive intervals.
But the psi here should be a particular state, only a ground state. For which psi is it true?
Yeah, the state. So yeah, the motivation for this equation was we started with thinking about the ground state of the CFT. Right. That was this formula here that we started with. Ooh, it's a true statement about the entanglement Hamiltonian of an interval in the ground state of the CFT.
And so how does it relate to the kernel of the density matrix? Because the kernel means that there are some 0 eigenvalues. So why is it the ground state which is in the kernel? I missed this simple point.
Oh no, sorry. Yeah, my statement about the kernel of the density matrix is it's some UV garbage. The kernel of the density matrix, right? Okay, wait, sorry, I didn't understand your question.
So the question is that somehow you said, okay, since there's a kernel, but the kernel is going to kill this psi anyway, so...
That's true for, that's not a statement about CFT ground states. Yeah, that's just a statement. So take some finite dimensional Hilbert space, think about pick a state, compute the reduced density matrix system region. If I act on the state, again, the kernel of the density matrix doesn't matter.
Okay.
Yeah.
Okay. Yeah, sorry.
Okay. Good. So, but indeed, the crucial point is that ground states of CFTs are special because they satisfy these very, very strong conditions, which is very surprising that in fact there are any solutions at all. And okay, so I said that this, so yeah, when I said that this statement is true, the previous one is not. Here's some evidence that it's true. If we compute the variance of this operator in the state, right here, this equation, it looks like the statement that the state is an eigenvector of k. But it's actually not a linear equation, right? Because k is constructed from psi. But if it's true, it means that the variance of the operator k, so think about, start with psi, construct k in the way that I described. It's this linear combination of entanglement Hamiltonians. It's some fixed operator on the Hilbert space. We can compute its variance on that state. If the variance is 0, it means that k of psi is proportional to psi. Right? So the statement is just that that this quantity, which is, it measures the violation of this statement, that k of psi is proportional to psi, it decays like some power law of the system size.
Why are you plotting the variance and not just the norm of the difference of the two sides?
Norm of the difference of the two sides. Yeah, you're right. This equation doesn't test what the coefficient is, but the coefficient is completely determined. Yeah, don't worry about that. Yeah.
So for this plot, how did you choose ABC?
I don't remember. It's not special. No. Yeah. Yeah. There is a question you can ask, which is there are sort of two versions of the statement. One is we could demand that the vector fixed point equation is true for a region of fixed size as I scale up the whole system. And that's actually a weaker statement than I demand that the vector fixed point equation is true for a collection of regions whose size is a finite fraction of the system. Both of them are true in the ground state. The weaker condition actually is also true for states, for example, that have twisted boundary conditions, things like that. Yeah, and for, okay, yeah. It's a less stringent condition. Okay, so I claimed that all of the universal data is in the reduced density matrix, but I didn't tell you what the universal data is. And I have to admit now, here comes the confession part of the talk, that I do not know the answer to that question. What is all the universal data? However, there's a way for me to cheat and show that this statement is true without answering that question. And the way is, I'm going to show you how from the state that we started with, from the reduced density matrix, you can reconstruct not only the whole state, but also a parent Hamiltonian whose ground state it is. We can reconstruct the Hamiltonian from the state, if it's a CFT, if it satisfies these conditions. Okay, so that's the next goal. So the first step is to reconstruct the ground state, and here I think it's a really quite remarkable fact. So I said earlier that this A1 condition that we imposed for liquid topological order ground states allowed us to merge regions. If we knew the density matrix on AB, we knew the density matrix on BC, and we know that it satisfies A1, we can uniquely reconstruct the density matrix on ABC. This vector fixed point equation, actually, well, okay, the operator version of this fixed point equation that I wrote is a generalization of that Markov condition. So if you ignore this term, so twiddle just means I subtract the expectation value. If you ignore the second term, so this is just a rewriting of that operator fixed point equation. If you ignore the second term, this first equation is actually exactly the same as this Markov condition. And so the vector fixed point equation is a generalization of this Markov condition, and well, just think about what this equation says. It says that if you know the reduced density matrices of the small regions, you can reconstruct the reduced density matrix of the big thing from them. So it's in that sense, it's a generalization of the Markov condition. Okay, so that's the idea of what I mean by you can reconstruct the whole state. We can also reconstruct the Hamiltonian. This is, I guess, the most important part. So here's the idea. So just as we could use these locally quadratic functions as a basis of functions to reconstruct the function 0 to cancel out the operator part, we can also reconstruct the function 1. So there's another linear combination of these functions, which is this one. So I wrote it just for the case where we have equally spaced intervals. But if I add up the beta for every 2 intervals and subtract from it the betas of every single interval, it's not too hard to see. Here's a picture of this is every 1 interval. Sorry, this is every 2 interval. This is every 1 interval. If you add them up, you get 1. And so if we take that corresponding linear combination of k's, I guess this is really the k twiddles, you get 1 integral of 1 times h, right, which is just the Hamiltonian. So if we really did have the CFT ground state in the continuum, we can reconstruct the Hamiltonian. And so we can just apply the same formula in the case of a well-regulated state that we're given. A few comments about the resulting operator. It turns out to be a combination of a certain, of what we call deltas, which is, it's the same combination of operators that appears in the A1 combination, if I replace the entropies by their entanglement Hamiltonians. And this combination of operators actually is positive. This is a theorem that David Lin proved with Isaac Kim and his collaborator, which is it's an operator form of Strong subadditivity, or of weak monotonicity, which is equivalent to Strong subadditivity by a purification maneuver. So that is to say that it's always bounded below this reconstructed Hamiltonian. And moreover, we can show that if the state satisfies the vector fixed point equation, it's the ground state of this operator.
Can you remind me, just from a formal point of view, so you said when you split the interval into these pieces, then you kind of have on every piece, you have an infinite dimensional, formally infinite dimensional.
In the continuum, yeah.
in the continuum. So this ki plus 1, it's some operator acting on this infinite dimensional tensor product.
This is the thing we're not supposed to talk about. Yeah.
Let me laugh for a second. So I just want to know: is there some perhaps we are lucky, and it's known that even in this infinite dimensional setting, this k is a bounded operator, at least on
I think the k itself is probably not, but this combination of k's is. Yes.
Okay, this combination is supposed to be bounded.
It's nice. Yes.
Okay.
It's a nice operator.
Okay.
Yeah. The crucial thing is that the bad stuff happens at the boundaries of the interval, and in this combination, every boundary of the interval appears equal number of times with opposite signs.
No, but we have to split. So normally, usually when people prove theorems about Hamiltonians, Hamiltonian, of course, has to be a sum of some operators which are bounded. So you're saying that
yeah, right.
a single term in the sum is bounded, or a single term?
Well, in a finite dimensional Hilbert space, yes, absolutely.
Yeah, finite dimensional, yes, but in infinite dimensional, not quite.
Is it bounded? I'm not sure if it's bounded, but it's something that they would allow us to talk about. It's yeah.
So you're somewhere on the path to enlightenment.
Say again?
You're somewhere on this path to enlightenment.
Yes, somewhere on the path. I hope. Okay. So yeah, I should mention that there's a similar formula to this for the other 5 global conformal generators, which I won't write down. And here, so here's I guess the real reason that you should pay attention to this, which is this. So here's what we did. Take the Heisenberg chain on 8 sites. This is actually maybe even overkill. And in red here is the spectrum of the original Hamiltonian, and the x's are the spectrum of this operator, constructed from the ground state of the Hamiltonian. And actually, so you notice that the normalization is wrong. That this is, I should say, periodic boundary conditions, right? So this is proportional to the spectrum of scaling operators in the C=1 theory at a particular radius. The reason that the spectrum is wrong is because of Heisenberg. It's his fault. It's not because of, yeah, so here we fix the normalization to match the original spectrum, but actually that was a wrong thing to do, because the multiplicative normalization of this operator, which actually I didn't write here, is completely fixed by this demand that these things add up to 1. And so actually without any input, if we hadn't changed that, the stress tensor would have been at 2, all the dimensions would have been in the right places. Okay, so here comes a nice surprise. This condition that we talked about, this vector fixed point equation, it turns out to be a condition that a certain function on the space of states has an extremum, has a saddle point. So basically this object here is just, in the linear combination that I took earlier, just replace every k with an s, replace the operator with just its expectation value. So this is just some function on the space of states. It's positive by Strong subadditivity. And the condition for it to have a saddle point, when you vary the state, is exactly this vector fixed point equation. And the value of the function at the critical point is proportional to the central charge with a known coefficient.
Sorry, I got that. Did k depend on psi, or is it not?
K is constructed from psi.
But then why is there no derivative on k or something?
Because the trace of the density matrix is 1.
Okay.
Yeah, it's you have to think about it a little bit. Yeah. Essentially, because the state is normalized. Yeah. Okay, so here's the conjecture. The conjecture is, so this is a picture of so here's the a slice of the space of states. This is a picture of this function on the space of states. The conjecture is that critical points of this function are RG fixed points.
Is it artist's impression, or is it an actual?
It's the actual thing. Yeah. And actually, yeah, David did an amazing thing. I mean, in addition to all the amazing science, he also did an amazing thing by finding a slice where 5 of the critical points can appear. So okay, so here's what the procedure that this leads to, and where this function comes from, where this picture comes from. So here's my Hilbert space, right? The Hilbert space lives in a circle. I'm going to divide it up into just 4 parts. So in the continuum, each of those 4 parts would be an infinite dimensional Hilbert space, And now I'm going to do something very extreme. I'm going to replace each of those infinite dimensional Hilbert spaces with a single qubit. Okay, so we have states. We're thinking about the space of states on 4 qubits, and I'm going to restrict this Hilbert space further. I'm only going to think about translation invariant states, because CFT ground states are translation invariant. And I'm also going to impose time reversal invariance just for convenience. I don't know if that's an important assumption yet. And just look for critical points of this function. Okay, so you can see 5 of them in this picture. Certainly the product state is a critical point. The cat state is a critical point where we get c equals 0. But in blue here, you can see that we meet some of our good friends. Right? So we find a critical point where the value of c that we infer from just the value of the function is a little bit bigger than 1/2. We find 2 more critical points where the value of c that we infer is a little bit bigger than 1. And then from those states that are critical points of this function, we can reconstruct a local Hamiltonian, right, by the procedure I described. A local Hamiltonian means it's, we have a Hamiltonian density, which we can then study on a larger system. And when we study the spectrum of the local Hamiltonian that we get from these 3 states on a larger system, we see that the spectrum is exactly the list of scaling operators of these 3 CFTs.
Can you remind me what is eta in your formula?
Eta is the cross ratio of the 3 intervals. So actually here, when we're taking these things to be of the same size, so eta is 1/2. Yeah. So actually, maybe it's worth mentioning the condition we're imposing. You can think of it either as satisfying the vector fixed point equation on ABC, or you can think about it just as minimizing the variance of the reconstructed Hamiltonian. AB plus BC plus CD plus DA minus A minus B minus C minus D. They're related by purity. Okay, so that you'll notice that there are some other fixed points which you should think of as as 0 correlation length fixed points, which we can identify again by studying the system on a larger, reconstructing the local Hamiltonian and studying it on a larger Hilbert space. And the thing we find is that there's some ground state degeneracy, which depends on the system size.
So what's the dimension of the space of states here?
The space that we're exploring, I think it's 5-dimensional, something like that. Yeah.
So that's a plane, just some.
This is a slice. Yeah. It's a very well chosen slice. Yeah. So for example, one of the fixed points that we find has the property that if you reconstruct the Hamiltonian and study it on a system of L sites, the ground state degeneracy is the Lth Fibonacci number. So it's the golden chain. It just comes out of this. Okay, so this is the case. This is if we replace each of those infinite dimensional Hilbert spaces with a single qubit. It's reasonable to ask what happens if we replace it instead with a 3-state system, right? And if we do that, we find a few more of our friends. We find, in addition, two more of the unitary minimal models, and we find some more points along the c equals 1 line. And actually, on my computer in my office, there's a list of wave functions of states satisfying this condition on qubits that our job this summer is to analyze and figure out who they are. And we're working our way past c equals 1 now, and we hope. And so I think it's plausible that we'll find irrational CFTs, maybe CFTs that people don't know about, or maybe the ones that people have recently discovered, like the one Antonio found. Okay. A few comments about this. So as I mentioned, the multiplicative normalization is completely fixed. So this is actually, it's a very useful tool if you're studying some one-dimensional system. It has a quantum critical point. You want to know what CFT it is. Previously, if I had to do this, I would have normalized the spectrum by finding the stress tensor and setting its dimension equal to 2. You don't need to do that. The multiplicative normalization is completely fixed. So you don't need to go all the way up to T. I claim that the reconstructed Hamiltonian from a given state is closer to the Platonic notion of the conformal field theory ground state than some random Hamiltonian that somebody wrote down for some reason. Then, yes?
Can you just remind me what the condition that you wrote here is? That
the normalization here? Yeah. So so the reconstructed Hamiltonian, remember, is the goal. The reason we chose this combination was to make these things add up to 1, so that K is So if I write this form, it'll be clear. So Ka is integral over the region, this function beta times the Hamiltonian density. Right? I want to add up a bunch of these, so that these things add up to 1. right? So that I get sum over I lambda I ki is instead integral dx h of x, right, which is h.
Yeah, you could have used linear elements and had a smaller footprint.
We don't get to pick what the functions are, right? John Carty picked the function, or I don't know, but these are not we can pick
Well, I mean, I
function.
know somebody else who picked them, but if you use linear elements, it would still add up to 1. I mean, these are quadratic elements.
The fact that we're using quadratic elements is chosen for us by the gods of conformal field theory.
Yeah. So it's
But it's
important.
not chosen.
Yeah, it's a fact. Yeah.
What causes that fact?
This basing on a Wickman formula, right? It's the fact that the entanglement Hamiltonian has this form. Right? So this beta is this.
So you needed this 3-region decomposition.
Well, yeah, the 3-region decomposition is chosen because of the form of these functions.
So this formula comes out with, so you take infinite, half infinite, half line, where this function PA is linear, and then you map to an interval.
That's one way to think about it. Yeah.
Okay.
I guess Carty and Tony actually did it by some replica calculation also.
I see. Okay, thank you.
Okay. So I claim that you pick some lattice model, find its ground state, use this procedure to reconstruct the Hamiltonian, and you get closer to closer along the path of enlightenment. Yeah, closer to the ideal CFT.
So does it mean that there are some irrelevant corrections that are going to be set to 0?
Smaller, yeah.
Smaller.
Yeah. So within the fixed Hilbert space size, there's a sort of smallest you can get, closest you can get. Okay, and then perhaps a more frivolous application. If you just plot the error of this vector fixed point equation, just the variance of the reconstructed Hamiltonian, suppose someone presents you with some model, and whose ground state you can find, but you don't know what it does. Just make a heat map of the error of the vector fixed point equation, and the places where it's small are fixed points. So for example, here's just I just picked some, I guess Xiang picked some random systems. Here's the transfer field Ising model with some y term. It actually has the phase diagram is round. In the middle is, what is it? The middle is the ferromagnet. This ring is a circle of Ising fixed points, and then the outside is the paramagnet. And so this is a plot of the central charge that you infer from the vector fixed point equation, and you see it has a maximum, which is somewhere around a half along this ring of Ising points. And here's a instead, let's think about the antiferromagnetic Ising model. Somebody mentioned this Hamiltonian earlier in the week. Who was it? I forget who it was. Was it Anders? Yeah. Oh, Andreas. Yeah, that's right. Okay. Right. So he mentioned that it has this circle of Ising fixed points, which is what you can see here, and where these two arcs where c is equal to a half. So it's a way to make a very quick but illuminating picture of the phase diagram. Okay. We're there. Okay. So now let's try to do it in 2+1 dimensions.
Just as when things are getting interesting.
Okay. So in any dimension for a round ball, as I emphasized, we know the entanglement Hamiltonian, where now this beta is a function which is locally quadratic, only non-zero on the interval. And again, we can look for linear combinations where we cancel the operator part, or we make the operator part add up to 1. Right? Unfortunately, or I don't know, it's a fact that now, in order to do this, we need not just 3 intervals, but in fact a continuum of balls in order to accomplish this. And well, let me just tell you what the best we've done so far is. Take 3 concentric disks on the sphere. I call them A, B, and C here, which I'll sometimes call it AI. I goes from 1 to K. And so we could take some linear combination of them. But then omega here, let's think of omega as specifying the center of all 3 of these disks. And the idea is just integrate over the center of the disks. And so the basic idea is that actually for any one of the regions, if you do this averaging over the center of the disk, the coolness functions add up to 1. You just get the Hamiltonian. So purely in the exact ideal CFT ground state, this would produce the CFT Hamiltonian. And then the goal is, the reason to choose these sum of things is to cancel the garbage. So the actual lattice Hamiltonian is not just the ideal CFT thing, but there's some additive stuff which is supported at the boundary and which we want to cancel by cleverly choosing these lambdas. Okay, and how do we check that it works? Well, we've checked it so far on the icosahedron, on the fuzzy sphere with orbital cuts, and on the fuzzy sphere with real space cuts. And it kind of works, actually. So, okay, so here's on the icosahedron, the way we define what we mean by the area is in this way. And actually, with this rule, it satisfies a pretty good area law. And in fact, even the value of f that we get from this is pretty good. It's this is no finite site length is just a fixed 12 sites. It's surprisingly good. And so what are possible balls on the icosahedron? It's you could take 1 or 3 or 6. If I compute the error of the vector fixed point equation as a function of the parameter, by which I'm just going to think of a linear combination of 2 of them, either 3 and 1 or 6 and 3, using this, our expectation for what I'm choosing this combination I want to choose this combination to cancel the area law contribution. The predicted value of the minimum of the error actually agrees with what happens. And so this picture is the analog of those heat maps that I showed. If we vary the transverse field in the transverse field Ising model, there are places where the error in the vector fixed point equation is smallest, which are the ferromagnet, the paramagnet, and near the critical point. And this is the reconstructed spectrum on the icosahedron from various combinations of these regions. It's not so bad. The orbital cut does quite a bit better. So this is the analog of that plot of I vary which linear combination of 2 regions I consider, and there's some value of x that we predict should be the minimum of the error, and it's pretty close. It sees where the critical point is, and here's a picture of the reconstructed spectrum. It's not as good as some of the plots, some of the spectra that we've seen this week by a long shot. But one thing I'd like to say is the blue stars, I guess they're kind of small, are a 0 parameter fit to the spectrum. So just like I was saying, you didn't need to determine the multiplicative normalization of your Hamiltonian by setting the stress tensor state to 3, 2 and 3 in this case. The multiplicative normalization here is completely fixed. It's just the output of what the spectrum is. Okay, so I guess I should wrap up. We have a little bit of a theory of what we're trying to cancel by taking these later combinations. Essentially, it's a generalization of this famous formula for the short-range entangled contribution to the entanglement entropy. It's sort of an operator version of that equation, and it seems to work. Okay, I'm going to skip that. And okay, maybe I'll conclude but with a little tangent, which is a question that I'm surprised that hasn't come up in this week-long meeting about the fuzzy sphere is, why does it work so well? Nobody said anything about it. And so let me tell you my opinions about why I think it works.
You mentioned a little bit about algebra.
Yeah, you said a little. Okay, you said a little bit. Yeah. So let me try to say a little more. So in addition, of course, it has SO3 symmetry. That's great. But I think, indeed. So Yunchen said a little bit about it. Yeah, it's true. It's true. The fact that it preserves the locality of the operator algebra, I think, is the reason. And there are 2 senses in which I claim this is true. The first is that there's a local Hamiltonian on the full Hilbert space. By the full Hilbert space, I mean this ideal continuum theory of, say, a fermion in the continuum on the magnetic field, which is, just here's a local Hamiltonian on the Hilbert space. The idea is we choose this kinetic term so that it has a minimum at some band that we like, and by choosing mu appropriately and picking this gamma to be big, the low energy theory is the fuzzy sphere Hamiltonian. So it's in this sense it is a local theory. In general, there's some degenerate perturbation theory that says that the effective Hamiltonian is the projection of the full Hamiltonian onto the fuzzy sphere, which is not quite the same as just plugging in the projected operators into the full Hamiltonian. This is supposed to say H full of psi. But in fact, for the transverse field Ising model, they are the same. Okay, and so it's worth noting that this property so far is shared by a lot of other systems. So for example, we could choose, instead of turning on a magnetic field, we could just choose this to be the ordinary d squared. And in this way, we could pick out, we could pick out some arbitrary number of spherical harmonics, right? We could pick just 1, we could pick 2, we could pick all the angular momenta up to some value. And this method was used recently to study the Gros-Neveu fixed point by folks at Berkeley. This method actually works, but it has the drawback that the number of orbitals jumps very quickly as you vary the maximum angular momentum. If we could use just one layer, it would actually be pretty great, because that we could do in 3+1 dimensions. But there's a second notion of the sense in which the fuzzy sphere preserves the locality of the operator algebra, which is that it does a good job of resolving the delta function, right? So if we compute this commutator on the fuzzy sphere, it looks like this. It's this beautiful smooth function that's localized near 0. If we do this with a single layer, actually it has the property that it also has a maximum at the antipode. So the single layer actually makes a fuzzy RP2, because your point and the antipode always have the same support. So that's why we tried 2 layers, and that does a little better, but it has this ringing. And with many layers, it looks quite a bit better. But none of these is as nice as that function. I think that's the real reason.
In principle, you could put a kind of soft cutoff, right?
On the angular momentum, yeah, we could.
Wouldn't be very nice for exact angulization, but maybe for some other methods.
I think that's right. Yeah, putting a soft cutoff would indeed, it would minimize the ringing.
In due fairness, we discussed the seasons 2 years ago, so.
Okay, I missed it. Okay. So actually, 2 years ago, what did people say about this possibility? Did you conclude that it wouldn't work?
Yeah.
It kind of works.
No, this was 2 layers we didn't consider. So.
For 1 layer, certainly will not.
Because of the.
More than it's like you cannot get the correct angular momentum also.
Okay. All right. So anyway, so I didn't say anything about the real space cuts. The shorter answer is we think it'll eventually do better than the orbital cuts, but there's a lot of stuff that we need to learn to remove, which I think we actually do know how to remove. But I'm not going to say more about it. Okay, so why did I do this? The idea is, starting with a model of the quantum critical point, you could do gradient descent on this function to move closer to the ideal CFT. It's maybe a lot of this week has been spent on talking about tuning to the ideal CFT. This is I think, somewhat systematic way to do it. I'm optimistic that by this method we can identify new CFTs, and I guess one very immediate application is Yin Chen wrote down this ansatz for the ground state wave function, and was, I guess it's fair to say, struggling to infer what the scaling dimensions it produces, and reconstructing the Hamiltonian and just computing its spectrum is a very direct way to do that. Okay, I'm going to stop there. Thank you for your patience.
What's the last slide?
What's the last slide?
Looks like there was some interesting comments.
Oh, okay. Yeah, so I just wanted to remind everyone of the central dogma. I think it's an interesting principle. So far, it's been applied to a few examples. I think it's sort of a fun question to think about what other categories of states one could apply it to. So fractons is one example that I think one could do, but I don't know how to do. Yeah, these are some other things I don't understand. And maybe it's worth mentioning there's a third kind of bootstrap that hasn't come up so much this week, which is the kind where you have a Hamiltonian and you want to find its ground state, and you do that by minimizing expectation values of the terms in the Hamiltonian. So the idea is you make an ansatz for the reduced density matrix, and use those as variational parameters to minimize expectation values H, but there's no guarantee that there is a global state whose marginals those are. And so if you knew somehow that it satisfied some condition, like the vector fixed point equation, you could guarantee that there was a state that had those marginals that minimize your expectation values. So I think this is a strategy that David has proposed to approach some difficult problems in mathematical physics. He's very ambitious.
It's published?
No. No, it's an ambition. It's okay for me to mention an ambition, I think. Okay.
a whole question about your last point. You were saying it's a better way to extract spectrum. So I think you still need to diagonalize this reduced density matrix somehow, or so it's much cheaper than to play with it than the original Hamiltonian find the excited state. So.
Is it cheaper? So wait. So what are we comparing? We want to compare it to like.
I mean, you said it's a better, but for me, better probably means faster. Algorithmically.
I don't know. I guess what I mean by better. Yeah, I don't know about algorithmically, but what I mean by better is the error in this vector fixed point equation is sort of a. I think it's a very principled sense in which the notion of how far the thing is from the true CFT ground state, because that should be exactly 0 in the true CFT ground state. Whereas I don't know, other cost functions like you pick some bunch of levels and ask that they be have an integer difference, seems like it involves some human input, more hyperparameters. I don't know. That's yeah.
Right. So presumably this principle you have for finding the Hamiltonian should give you the correct substance that you can spread on any manifold and give you the right spectrum.
That's right, because it's a local Hamiltonian. Yeah, you can put it wherever you want. Yeah, yeah.
But we are not guaranteed that the model Hamiltonian is local beyond CFT. So can we do conformal perturbation theory or something to estimate DR or subfinite size?
Well, hold on. So when I say it's so in one plus one dimensions, I can make a strong statement. So my reconstructed Hamiltonian is local because it's K2 minus K1, right? It's made only from 2 sites and 1 site. So in fact, it's always a nearest neighbor interaction. Yeah. So right. So within the site, I'm not looking. Yeah, you're right. It might if I just pick some random state and reconstruct the Hamiltonian, it won't be local within the site. But that's what I'm calling.
So is there a way to do conformal perturbation? Finite size, you will not saturate your equality. So can I do conformal perturbation theory to understand any state?
To understand the errors. Yeah, I see. I think that's a very interesting question. I don't know. Yeah.
Actually, on that point, the numbers that you get, are they bounds? Are they, I mean, thinking of bootstrap.
Great. I also don't know the answer to that question. Yeah, it's a few things. I have opinions about a few things. So one is when we extract the central charge from the right-hand side of this vector fixed point equation, I think it's always an overestimate of the central charge. And actually, there's a different calculation which I believe is always an underestimate. I don't know how to prove that yet, though. I think, yeah.
Sorry, actually, so if you were to do this this minimization to find Hamiltonians, like, do you think you would be able to distinguish between the Ising CFT and the Ising star CFT on a sphere? And if they would have different ground states and something like that?
The ground states will definitely be different.
Okay,
yes. Yes, that's right. You can extract the spectrum of anions from the reduced density matrix of the ball. That's right. Yes.
What was the numerical example? The Heisenberg chain? You did that. That was the example in 1 plus 1 you showed. So what size are you taking the regions to be?
I don't remember. I think maybe it was. Well, there aren't many choices, right? Because it was only 8 sites. So I think maybe it was 2 and 2 and 2. Yeah.
Can you look directly at what the Hamiltonian is it produces? I mean, in terms of
its
operators.
In fact, in that case, it is the Heisenberg Hamiltonian.
You get that guy.
Yeah.
Okay. And also in your 4-site examples, you have a list of examples that you mirror, and one of them was ferromagnet.
Yes.
What did it mean exactly?
What did that mean?
Just like the SO3 invariant ferromagnet.
Yeah, that's right.
So that has degenerate grounds.
Yes. Yes.
So what are you getting in your calculation?
It's exactly the the ideal ferromagnet Hamiltonian. Yeah, just S dot S. So yeah, so.
I'm getting one of the ground states of that.
No, it has a degenerate. So yes. I see. You're saying which one is the fixed point? Yeah. No, that's right. Oh yeah, I should say the minima of this function are actually orbits of local unitaries. Right? There's because the function we're minimizing is invariant under local unitary rotations, and so in fact, yeah. So all of the ground states of the ferromagnet are fixed points. Yeah.
Okay, and why do those things come up? Because it's obviously not a CFT, right?
It's a CFT. It's just a gap CFT.
But isn't any? I mean, then you could have any product state as a CFT.
Product state, yes, that's right. Yeah, I wrote the conjecture carefully, right? So critical points of this function, I think, correspond to RG fixed points, which include both infinite correlationally fixed points and zero correlation fixed points.
But you have a value of C, which is not trivial.
What the value of C means, I don't know, actually.
Yeah. Even if it's a product state, it can be.
No, for product states, you get 0. But for these other gap fixed points, you get some value of C, which so for example, if you study in a larger system and compute C for different regions, you'll get different answers for different regions. Whereas for a real CFT, you get the same C, whatever combination you choose. So we can tell the difference. Yeah.
Can you tell me, was there a similar kind of support that you use on the sphere to project the sphere? I didn't get the shape of that support.
Yeah, so we're choosing 3 regions which are concentric disks, concentric round disks, and then averaging over the center of each of them.
Averaging? What do you mean by averaging? So
integrate.
Integrate the solid angle over that.
Integrate the right. So
what's the shape?
So yeah. Here's the formula is it's a sum of these things which there's 3 terms in that sum over I, and then for each I we integrate over this. Omega is the location of the center of the disk. So the formula in 1 + 1 dimensions was sum over all 2-site regions minus sum over all 1-site regions. So this integral is the analog of that sum. So we sum over the whole space.
But it's a continuous sum over that.
Yeah, actually, and so in the numerics we do that integral just by group theory, right? Because we know the rotation generators. Yeah, we don't need to actually do an integral.
Why do you need 3 and not 2?
Great. Okay, so good question. We think we need 3 because of the following logic. So in practice, already 2 does well, but we don't understand why it does well. So here's here's a quick argument. A TQFT is a special case of a CFT, right? It's invariant under conformal transformations. For TQFT, we also have a formula for the reconstructed Hamiltonian, and basically because of the, what is it called? Whose formula is it with the F minus E plus V? Euler? Yeah.
Euler calculus.
Yeah. Right. Because of that, it involves faces and minus edges plus vertices, which is 3.
So you must be sensitive to each of those things.
You need all 3 of them to get the right answer. Yeah. And so in the case of TQFT, we don't need to pick round regions, so we actually know how to do this. But it because we need 3 in the case of TQFT, we think we need 3 in the case of CFT. That's the short answer, but there is a slightly better argument, which is explained on the slide, which maybe we shouldn't explain. Yeah.
Okay.
Everybody happy? Okay.